Hello and welcome to Introduction to Academic Research. My name is Ben, and today I will be talking about sampling distributions. Now, if you have already been doing the reading for today's session, then you will probably have stumbled upon a phrase, the mean of the sampling distribution of the sample mean. Now, if you're like me, then the first time you read this, you would probably have thought something like, what the hell is going on? So the goal of today, the main goal of today, is to make sure you understand what that word means, and I will guide you towards it in a very slow, step-by-step way, in the hopes that you will see what that is for and what we can do with it. So the themes for today are: first, I'm going to discuss some basic concepts, and the one I just mentioned is one of them. Then I will be discussing some mathematical facts that have wide application in statistical work. And then in the end, I will show you how we can actually apply these mathematical facts. Good. Let's start with the basic concepts. So the first thing I want to talk about is samples. Now, this is not something new. Assume you have a population of 4 people and you want to draw a random sample of 2 people from your population. So a random sample with a sample size of 2. Now, of course, this never happens in real life, right? Populations are much bigger and samples are much bigger and so on. But we'll just use this very, very, very simple case to illustrate the concepts we need to understand. So if I want to draw a sample of sample size 2 from those 4 people, then, for example, I could end up with a sample that includes the yellow and the red person. I could also end up with a sample that includes the green and the blue person, or a couple of other samples as well. Now, these people have properties, right? In this case, we might be interested in the age of these people. I have indicated the age of the people in the population by the numbers here next to them. So the yellow person is 18 years old, the red person is 19 years old, the green person is 20, and the blue person is 21 years old. Now, in addition to asking questions about individuals and what kind of properties they have, we can also ask questions about the properties of samples. And those are then called sample statistics. So a sample statistic is a property of the sample, for example, the mean age of the people in your sample. So for example, here we have the sample of the yellow and the red person, and the sample has a property, namely the mean age of the people in the sample. And in this case, this property is 18, so the mean age is 18 and a half. So the mean age of the people in the sample are 18 and a half. And this is a sample statistic. Now, in this course, we will limit our attention to sample means. That is, we will always ask questions about the means of a sample. Now, the next thing I want to talk about is random sampling. So if I draw a sample at random, then this is basically similar to throwing a die, right? I can just end up with different outcomes, and I can think about how likely it is that I end up with a specific outcome. If samples are taken truly randomly, then every sample is equally likely to be chosen, right? So if I take samples randomly from this population, then the chance to get a sample with the yellow and the red person is the same as the chance to get a sample with the blue and the green person in it, right? So every sample has the same chance, every possible sample has the same chance to be selected if sampling is truly random. However, the sample properties might be a little bit different in that respect. For example, in this case, in the particular case we are looking at, there's more samples that have a sample mean of 19.5 than there are samples with a sample mean of 20. And that means even though it's equally likely to select each individual sample, it's more likely to select a sample with a sample mean of 19.5. And this is something that's important to keep in mind and will be important later. So if we were to ask the question kind of how likely it is to get this or that sample, right? What's the probability to get this or that sample? That's not super interesting question because, as I said, the sample for the probability for each sample is the same. But if we ask what's the probability to get a sample with a specific sample statistics, for example, a specific sample mean, then the question becomes much more interesting. And this question is answered by what is called the sampling distribution of the sample statistic. So the sampling distribution is basically just a probability distribution. It's, in a way, a list of the probabilities to get samples with a specific statistic. So as I said here, remember the sample statistic is a property of the sample, and here we are only interested in the sample mean. So the sampling distribution of the sample mean would tell us how likely is it to get a sample where the sample mean has a particular value, for example 20, right? We can ask what's the probability to get a sample with a sample mean of 20? What's the probability to get a sample with a sample mean of 19.5, right? And the answer to these questions is given by the sampling distribution for the sample mean, for example. So the sampling distribution of the sample mean simply tells us how likely is it to get a sample with a particular mean. Okay, now get ready for this horrible phrase I mentioned in the beginning, the mean of the sampling distribution of the sample mean. So the mean of the sampling distribution of the sample mean is the average sample mean that you get when you draw a sample. So assume that you constantly draw many and many and many samples, and each time that you draw a sample, you take note of the sample mean, and then you take the average of all those sample means, and that then is the mean of the sampling distribution of the sample mean. And this is an important concept because it tells you kind of what you can expect the sample to look like when you take a random sample. So assume you are about to take a random sample, right? And then you wonder, well, how is the sample going to look like? What's the sample mean going to look like when I take the sample? And that's what the mean of the sampling distribution of the sample mean tells you. Now, why would you be interested in knowing how likely that is to get a sample with a particular sample mean? We'll get to that later, but in a way, if what we actually find is very much different from what we expect, then this might show us that some of our assumptions about the population or about samples are wrong, right? And we'll make use of that in statistical testing and so on, right? If we have a hypothesis about how the age, for example, in a population is distributed, and then the hypothesis will tell us something about how samples are likely going to look like if we take a sample, and then we take a sample and a sample looks very, very different, then maybe something with our initial hypothesis is wrong. But we'll get to that later. This is just as a teaser for why we are interested in this weird concept. Okay, so this concept, the mean of the sampling distribution of the sample mean, is quite a mouthful. You probably still struggle a little bit to understand it. So I will walk you through it in a more colorful way, a little bit slower. So here you have all the possible samples that we could draw from our from our small population. Now, with larger population, you will have many more possible samples, but I chose a population so small that I can actually fit all the possible samples on the slide. So those are the possible samples that you can get when you draw a sample of size 2 from the population. And now each of these samples will have a sample mean, right? So the first one will have a mean of 18.5, right? The average the average of 18 and 19 is 18.5. The second sample will have a sample mean of 19, right? So the average of 18 plus 20 is 19. The next two samples will both have an average of 19.5. So the average of 20 and 19, as well as the average of 18 and 21, are both 19.5. And then the other two samples also have a sample mean that is 20 or 21.5 respectively. Okay, so all the samples have a sample mean. A sample mean, as I said before, is a sample statistics, right? It's a property of the sample. And now we can ask ourselves, well, how likely is it to draw a sample with a particular mean? And this is given by the sampling distribution of the sample mean. And here I put in all the probabilities for drawing particular samples. Drawing a sample with a sample mean of 18.5, the probability is 1 in 6. Drawing a sample with a sample mean of 19 is also 1 in 6. But since there's two samples that have a sample mean of 19.5, the probability to draw a sample with a sample mean of 19.5 is slightly bigger. It's 2 over 6, and so on, right? So the sampling distribution of the sample mean simply gives you the probabilities to end up with a sample with a particular mean. Now the last step is to say, okay, now I know how likely is it to draw particular sample means. If I do this a lot of times, what's the average sample mean I'm going to get? And that's what the mean of the sampling distribution of the sample mean tells you. In this case, it is 19.6666. And we calculate this. This is just an expected value. We discussed before how you calculate it. You multiply the probability to get a specific outcome with the particular outcome. So here, the probability of 1 over 6 to get a sample mean of 80.5, right? So this is given by this here. And then you add to that the same for all the other possible outcomes. So the outcome that the sample mean is 19 multiplied by the probability to get the sample mean of 19 plus the sample mean of 19.5 multiplied by the probability to get the sample mean of 19.5 and so on. And then this is 19.6, and that is the average sample mean you would get if you draw a sample from this population with a sample size of 2. Okay, so I hope this illustration was able to take away a little bit of the terror of this expression, the mean of the sampling distribution of the sample mean. Let's look what we can do with it. So there's a couple of interesting mathematical facts that we need to be aware of. And these mathematical facts have to do with the relationship between the population and the sampling distribution. And these facts that help kind of make this relationship, they are very important because they allow us to draw inferences from population to samples and vice versa. Now, why is that important to be able to draw inferences from populations to samples and the other way around? Well, this is basically what statistics is about for a large part, right? So very often we are interested in properties of populations, right? We call them also population parameters, but we cannot investigate the whole population completely because the population is too large. Think about, for example, the population of Dutch citizens or something like that, right? Even though the Netherlands is a small country, you still can't talk to all 17 million people to learn something from them, right? So what we need to do is we need to draw a sample and try to learn something about the population from the sample. So we need to make an inference from the sample to the population. So more specifically, you might be interested in how are people going to vote in the next election? Do people tend to adhere to specific corona measures? Will people spend more money next year? Do people like a new product you would like to launch or something like this, right? And you want to know this for the whole population. You want to know how everyone votes, not just 10 or 20 people, but you cannot ask everyone. So you ask the people in a sample and then you make an inference from the sample to the population. And for these types of inferences, we need to know the mathematical facts that we are now about to discuss. So fact one is that the mean of the sampling distribution of the sample mean, so this very long, weird concept that we introduced before, this is actually equal to the population mean, right? And that means that if you were to kind of very often take samples, calculate the means, take the average of that, then that is what you end up with is just the population. This also means that sample means are a good way to estimate the population, but we are going to get back to that a little bit later. Now, I'm going to skip over fact 2 that was discussed in the script because we don't need it so urgently, but I want to talk about fact 3. And fact 3 says something about the relationship between the standard deviation of the sampling distribution and the population standard deviation. And the population standard deviation is equal to the standard deviation of the sampling distribution is equal to the population standard deviation divided by the square root of the sample size. That means that the larger the sample is, the smaller will the standard deviation of the sampling distribution be. Fact 4 says something about whether or not the sampling distribution is going to be normally distributed. And fact 4 says that if a particular variable is normally distributed in the population, then the sample mean of that variable is also normally distributed. Okay, so these three facts sound very abstract, and I would also like to illustrate them with some pictures. So assume you know what the population distribution looks like, right? So the population distribution is this blue line here. And assume that we know that this population distribution is normal, which is the case for a large number of interesting variables, or at least approximately the case for a large number of interesting variables in a population. Then we can make use of these three facts to say something about, it says here about the population distribution, but this should say about the sampling distribution. Good, and what can we say? Well, the first thing that we can say is what fact 1 tells us, and that is that if the pink line here is the mean of the population distribution, then this will also be the mean of the sampling distribution. So the sampling distribution has the same mean as the population distribution. Now, fact 4 tells us that since the population distribution is normal, the sampling distribution is also going to be normal. So that means the sampling distribution is going to be looking somewhat like the red line here. It will also have the peak where the purple line is, and it will also have this bell-shaped curve. Now the last fact, fact 3, tells us that the sampling distribution will have a smaller standard deviation because we have to divide the population standard deviation by the square root of the sample size. So it's going to be smaller. And that in fact means that the sampling distribution will be more peaked than the population distribution. So the population distribution will be flatter, the values are more spread out, while the sampling distribution is more dense around the mean. So those are the 3 facts illustrated. There's one more fact which is important, and that concerns the case in which the population distribution is not normal. And that is fact 5. Fact 5 says that even if a variable is not normally distributed in the population, the sample mean of that variable will still be approximately normal if the sample size is large enough. Now, what does it mean that it's large enough? We typically assume that to be the case for samples of size 30 or larger. Now, this is just approximately normal, but for all intents and purposes, that's typically good enough for statistical analysis. Now, how does it look like in a picture? Assume the population distribution looks like this, right? So this is certainly not a normal distribution. But if we take from this population a sample with a large sample size, maybe 100, then the sampling distribution will still look approximately normal. So it will look something like this. It will also still have the same mean. So the mean is the gray line here. And yes, it will have a smaller standard deviation, but that's a little bit harder to see in this picture. Good. Before we look at some applications of how we can make use of these facts, I would like to kind of remind you of what it is that we are looking at here, right? So the blue line, the population distribution, tells you what the probability is to select an individual person from a population with a particular property. So assume we are talking about, I don't know what, age again, something like this, right? Then we can ask, well, what is the probability that someone is, that we select someone from the population between this and this age, right? And that will then be given by the area underneath the density curve for the population distribution, right? The green area. In case of the sampling distribution, what we're looking at is, well, how likely is it that we select a sample where the sample has a particular property? For example, what is the probability to select a sample with a mean age of between 16 and 17? That would be given by an area underneath the red curve. So for example, if we're interested in, well, what's the probability to find a sample such that the sample mean is between these two values, right? Then this is given by this weirdly colored orange thingy. Okay, so this is what we are looking at. There's 2 different types of distribution. One tells us something about how likely it is to get an individual with a specific property for example, in age. The other one tells us how likely is it to get a sample with a particular property, for example, mean age, right? And it's important to keep these two things apart. Okay, so let's look at some applications. Now, assume for a moment that we know how the population distribution looks like. We can then use the 4 facts that we discussed before to determine how likely it is to draw a sample with a particular mean. And as I hinted at before, this can be useful for all kinds of ways to think about whether our assumptions about a population are right. If we expect a sample to have a specific property and we find a sample that is very unlikely to be found, right? It's assume we figure out that the probability to draw a sample with a specific sample mean is nearly 0, and then we draw a sample like this, then that tells us that some of our prior assumptions might have been wrong, right? Or that we just ended up having a very unusual sample. That's also always a possibility. Good. So assume we have a population of UCG students where age is normally distributed with a mean of 21 and a standard deviation of 3. Now, if I were to take a sample of 9 students, what then is the probability to find a sample mean that lies, for example, between 19 and 23? So this is the type of questions we can answer with the mathematical facts that we have acquainted ourselves with. Now, the first thing we need to do is, because we want to know something about the probability of a sample, that means that we don't need to look at the population distribution, right? That gives us probabilities to find individuals. We need to look at the sampling distribution, which tells us how likely it is to find samples with particular properties, such as the property of having a mean between 19 and 23. So how does the sampling distribution look like? Well, we figure that out with the 3 facts that we have been discussing before. Fact 1 tells us that the mean of the sampling distribution is equal to the population mean. The population mean is 21, so the mean of the sampling distribution is also 21. Now, fact 2 tells us that the standard deviation of the sampling distribution is equal to the population standard deviation, this thing here, divided by the square root of the sample size. Now, the sample size is 9, the population standard deviation is 3, the square root of 9 is 3, 3 divided by 3 is 1, so the standard deviation for the sampling distribution is 1. Okay, so this is how we apply fact 2. This is something that you will have to frequently do in exercises and very likely also in the exam. Now, by fact 4, we know that the sampling distribution is normal because the population distribution is also normal. Okay, so in other words, the sampling distribution will look something like the picture on this slide. And since the sampling distribution is normal, we can use the 68, 95, 99.7 rule, which we introduced last class. So how do we apply it in this case? Well, 19 and 23 is 2 standard deviations to the left and to the right of the mean 21. And that means by the 68, 95, 99.7 rule that the probability to select a sample within this interval is 95%. Now, typically, of course, we do not know what the population distribution actually looks like, right? But fortunately, what we can do is we can reverse this type of reasoning we did now, right? So today we kind of mostly we focused on how can you infer what a likely sample is going to look like based on your assumption about the population. But as I already hinted at multiple times throughout this lecture, is that we can reverse this reasoning. We can think about, well, if it's so and so likely to find this and that sample, and we actually found that sample, what does it tell us about the population? And this way of thinking is what we are going to be discussing throughout the last 2 sessions of this course. Good. That's it for today. Thank you very much, and see you next time.